occur pretty well. But then at larger radii, the velocity stays large when it's supposed to drop off. And that's the signature that there has to be additional matter in a halo surrounding that galaxy. So there's some kind of dark matter around this galaxy that extends out to much larger radii and allows the velocity of the stars in the galaxy to stay large, even though we can't see this mass. So there's some kind of mass that has a gravitational force attached to it that's dark, that's something that we can't see. So another line of evidence for dark matter comes from gravitational lensing. So this is the idea that it comes out of general relativity, where mass and energy are equivalent, and so even light, which is traveling the fastest speed possible and has no rest mass of its own, because it carries energy, it responds to gravity, and so the path of light can be bent in the presence of other mass. So if there's some background galaxy behind a galaxy cluster, the huge mass of the galaxy cluster can bend the rays of light from that background galaxy and distort the images of that galaxy, or even give you multiple copies of that image. And so you can use the resulting image to infer properties of the galaxy cluster. And what you tend to find is that the galaxy cluster has to have a lot more mass associated with it than you can account for just from the stars. And so again, there's evidence for dark matter. So this is an example image of a background galaxy, and it's difficult to see multiple images, but you can see that a lot of these galaxies are kind of stretched and elongated, and that's this gravitational lensing going on, kind of distorting these galaxies, stretching them into funny shapes. So that gives us some evidence for dark matter, and now we can talk a little bit about what properties it must have. It has to match the amount of dark, the relative, what we call the relative abundance, the density of the particles. Soon after the Big Bang, when the universe was expanding and cooling rapidly, dark matter, we think, is a relatively massive particle, and so it would have kind of dropped out of thermodynamic equilibrium with the rest of the constituents of the universe fairly early on. And so we have an estimate from other cosmological measurements of how much dark matter there must have been in the early universe. And so whatever particle we can identify to be the dark matter must have the properties to give us that density. It has to be stable at the universe's lifetime scale. So it doesn't have to be stable forever like a proton, but should have a lifetime that's long compared to the age of the universe. It's massive and it feels gravity. We think it also feels the weak nuclear force, but not electromagnetic interaction. So it doesn't have an electric charge. So that's why it's dark. If it had electromagnetic charge, it would emit light or absorb light. That doesn't seem to be the case. It shouldn't significantly affect the synthesis of elements in the early universe or the evolution of stars. And it should be able to reproduce the structure formation that we see over time in the universe. And it should be something that we can verify experimentally. Whatever we propose for the dark matter particles, it should be something that has properties we can go look for, experimentally, and try to verify that this is a true theory. So there's many candidates that theorists have come up with. They go by a lot of different names: neutralinos, sterile neutrinos, Kaluza-Klein particles, neutrinos, actinos, gravitinos, and so on. And I don't know the details of any of these candidates. All I know is these sort of general properties, and then what to go look for experimentally as an observer. In general, we think that the dark matter is some kind of weakly interacting, a weak nuclear force, massive particle. Why a WIMP? It's neutral in color. That means it doesn't seem to have the strong nuclear force. And it's neutral in electric charge. But it does feel the gravitational and weak forces. So it feels, we think it has 2 of the 4 fundamental forces. And then it's stable and massive. And so this is a plot of interaction cross-section as a function of particle mass for a bunch of different possibilities. WIMPs are relatively high in mass and high in cross-section. And the neutralino is one of the archetypal examples of a WIMP. So we like neutralinos for a number of reasons. We have a standard model of particle physics that does a great job of describing all the particles that we can generate in particle accelerators. And you might have heard that a year ago, last summer, at the Large Hadron Collider, they presented evidence that they had discovered the Higgs boson. This was the last missing particle in the standard model of particle physics. So we have this beautiful model to describe particle physics. There are some indications that it is clearly incomplete, and you have to go beyond it. And supersymmetry, or SUSY, is a very popular extension of the standard model of particle physics. And supersymmetry predicts a whole second set of particles that go by funny names like neutralino. So this would be the lightest stable particle in this extension of the standard model, and it makes it a natural candidate because its mass and its cross-section work out well to meet the amount of dark matter that we need. And the thought is that from accelerator experiments, it doesn't seem to have a mass lower than about 50 billion electron volts. So its mass must be larger than that, and that puts it into a range where it might produce signatures in gamma rays. So we can do indirect searches for these dark matter particles using gamma rays. Okay. So how do we go about detecting dark matter? There's 3 different avenues, 3 different approaches we can take. They all have strengths and weaknesses. They all kind of attack different parts of the problem. And so different groups of physicists are working on all 3 approaches. So the first thing we can try to do is try to make our own dark matter particles, directly produce them in particle accelerators. The way you do that is you go to a large accelerator like the Large Hadron Collider, which takes protons at extremely high energies, in that case 4 TeV on each beam right now. And you collide them together, and that releases an enormous amount of energy, and that free energy is available to make different kinds of particles. And in some cases, rare cases, it makes Higgs bosons. Most of the time, it makes standard model particles, other protons and neutrons and electrons. The hope would be that you produce some dark matter particles. The tricky bit, though, is that the dark matter particle, it only interacts through the weak interaction in gravity. So it's very unlikely to leave any kind of experimental signature in your detector, other than you had an event where there wasn't enough energy that you detected afterwards. So the dark matter particle would escape your detector, and so you would have an event that looks suspicious because the energy you started with was not equal to the sum of all the products you produced. And so from that, you would have to infer that, okay, you must have produced dark matter. Unfortunately, the standard model has other particles that can do the same thing, like neutrinos, as opposed to just neutralinos. And so this technique has a very large background. So this is a very challenging way to study dark matter, but certainly worthwhile, because it gives you if you can measure this missing energy, if you can see that there's missing energy, then you get a direct measurement of how massive the particle is. Okay. Making it a little bit easier is direct detection, or direct detection. So you can build some kind of detector and bury it deep underground to get away from various kinds of radioactive backgrounds, and wait for one of these WIMP particles to come along and bounce off a nucleus in your detector. So a single particle, dark matter particle comes in and bounces off the nucleus of a single atom, and that nucleus recoils, having gained some energy. look at how much energy it gained on the recoil, and use that to estimate the mass of the dark matter particle. The thing is, the energy deposited is something like 1 to 100,000 electron volts. So it's a very small amount of energy compared to the mass of the nucleus sitting there. So the kinds of detectors you need to build for this are incredibly sophisticated. In many cases, need to be cooled down to cryogenic temperatures to be able to see this small amount of energy that's deposited. So it's technically very, very demanding to do this. There's a number of different approaches that people are taking. This is a global industry to try to do this. So you can, when that energy is deposited, when that nucleus recoils, you might produce scintillation lights in your detector, or phonons, which are kind of sound vibration in your detector, or you might ionize an atom and have some electrons sitting out, or you might use the energy deposit to see bubble nucleation and have little bubbles forming your detector. So there's a bunch of different ways to try to take that small energy deposit and produce a signal that's detectable in different ways. And so quite a few different experiments are exploring all these different words here, different acronyms for different experiments. We're going to try different techniques to search for dark matter through this method. So at the current moment, the best results we have searching for dark matter come from an experiment called Xenon 100. This is an experiment that uses liquefied xenon on the order of 100 kilograms of it, and looks for dark matter to bounce off the xenon nuclei and produce some scintillation light. And so this plot shows the scattering cross-section is a function of WIMP mass, and the green and yellow band here is the upper limit from the experiment. So they haven't seen anything yet, and they're saying that, okay, at a given mass, say 20 GeV, the cross-section for scattering has to be less than 10 to the minus 44 to the minus 43. And these ray contours over here show some theoretical predictions of where dark matter might be. So at least they're reaching a point where they're sensitive enough to probe where theorists think if there are dark matter particles that would interact in this way and where they might live in these parameter space. There's also another experiment called Gamma Libra that has been looking at dark matter using a different technique over many years, and they've seen annual modulation in the signal. And they say, okay, well, if the Earth is going around the sun, and the whole solar system is embedded in some dark matter that's moving with some random, some bulk velocity, then as the Earth moves around the sun, the relative velocity between the dark matter and the Earth is going to change. And that will change the rate of detection in our experiment. So if we see an annual modulation, then that should be a signature of dark matter detection. Unfortunately, there's a lot of things that change over the course of the year, like the temperature. So nobody else has been able to reproduce that result yet, so it remains a bit mysterious. So the last method of dark matter detection is indirect detection. And here the idea is that we know that there are dense regions of dark matter in interstellar space, such as near the center of our galaxy. And the basic idea is if you have two dark matter particles, if they can annihilate with one another and create particles that are more conventional, quarks and leptons, electrons and protons and neutrons, some of those particles will end up producing gamma rays. And those gamma rays will travel from where the annihilation happened to Earth, and we can look for that gamma ray signal and look for a signature of dark matter. There's a bunch of different particles that can be produced: positrons, electrons, neutrinos, antiprotons, protons, and it's worth